Well, thank you so much, Johan, for the invitation. It's great to see so many friendly faces here, if only virtually. I hope maybe next time when we get together, uh, we'll all be behind us and we'll be in person. So I'm excited to talk about some considerations across design and control for contact-savvy robots. Johan had asked me specifically to talk about some of the design stuff that I'll be speaking on from some of my postdoc work, and then transitioning to some of the work I've been doing at Notre Dame. So the one of the benefits of being on Eastern Standard Time is that I get to go first. The other benefit is that if you all disagree with what I say for the rest of the day, it won't hurt my feelings because I'll have to go to sleep here sometime soon. So I'm sad I'll be missing some of the talks, but looking forward to catching them on YouTube hopefully later. So before I jump into my my topic for today, I'd just like to plug some of the work that I'm doing kind of more broadly in my lab, the Robotics Optimization and Assisted Mobility Lab, or ROAM lab, at the University of Notre Dame. And so work in my lab is focused on advancing mobility for legged robots broadly defined, both quadrupeds and humanoid robots. And we're looking to advance these technologies so that legged robots can go anywhere on land. And we're looking to translate those technologies into assistive devices so that people can go anywhere on land, even after they've had an injury that might otherwise limit their mobility. So we're looking at problems in exoskeleton intent detection and looking at translating some of our reduced order control designs from bipeds and quadrupeds over to the prosthetics side. So, I'll be mostly focusing on this left-hand side today, but I hope down the road we might be able to talk about some of these applications on the right-hand side and some discussions together. Okay, so turning to our matter at hand, let's talk about contact-savvy robots. So I'd like to show here a video of Cheetah 3 handling this set of stairs blindly. So Cheetah doesn't know here that these stairs are in front of it. Instead, it's using some proprioceptive actuator technology that I'll be telling you about in order to essentially feel that it's touching down, and then to adjust its model predictive controller in order to recover balance for the torso. And so as Yuan had motivated, I think this ability to manage dynamic contact transitions, detect impacts is really of fundamental importance as we look to send robots beyond the lab. So whether it's a robot that's supporting our troops or going into a disaster zone, the scene of a fire, or into our homes, these systems are going to bump into objects and people that they didn't anticipate. And so this ability to kind of gracefully handle unexpected contacts and unexpected physical interactions in particular is quite important. And so the main thesis of my talk today is that essentially this problem, even though we often think about controlling these interactions from a control side, that it really is a coupled problem across both design and control. And I see a lot of motivation for that from biology and seeing how animals in nature handle unexpected physical interactions. So to motivate this is one of my favorite videos. This is from Bob Full at Berkeley. So he had this cockroach run across this gel surface, and they were able to measure the forces under the feet. And here, as this cockroach runs along, the unexpected physical interaction is that there's actually a little tiny cannon that's mounted on the back of the cockroach that's going to apply a disturbance force to the body. And so the kind of beautiful thing that they found when analyzing the ground force data following this disturbance was that the forces that were under the feet of the cockroach were, one, stabilizing to help recover its posture, and two, they occurred faster than could have possibly happened through closed loop neural feedback. But that's to say that there's something with the body of the cockroach that had passive dynamics engineered correctly to help reject this disturbance. And so I think in terms of managing unexpected contacts, it's really a combination of kind of brain and body. Here we see the body side, but of course, as we go into more challenging environments, there is a cognitive aspect, and there's no denying that. So, here for this baby ibex, the dynamics of its muscles and tendons and ligaments are providing some passive dynamics that help to make its motion efficient, but there's definitely a cognitive aspect in terms of planning its motions. So, as we look to send our robots into these types of situations, I'd like us to think both about the design side, the control side, and really how these two come together to make our system perform at its highest levels. So in terms of where I'll be going today, I'm going to first talk about some of the actuator paradigm that I've been using in my research, these proprioceptive actuators. And I'll acknowledge this is really the brainchild of Sang-Bae Kim from almost 10 years ago at this point. And so much of the credit for the original idea, all the credit for the original idea goes to him. So we'll take a look at that and look at why I think these actuators are ones that we should consider integrating into our robots that are undergoing contacts. And then we'll take a look at some of the motion generation aspects with a mini cheetah robot that I have done in my lab, some new strategies for trajectory optimization with hybrid systems. This is some work with my student, Lee. Then after we've talked about design and some of these control aspects, I'd like to talk about some more preliminary work that's going on in my lab, where we're trying to design robots that are easier to control by trying to formalize how we can engineer passive dynamics by looking at design and control together. And this is some work that's in collaboration with my student, Gabriel Bravo and Andrea Delpret. So let me first jump into this actuator analysis part. So here's an early video of one of the proprioceptive actuators, the first one that Sang-Bae built actually before I was in his lab as a postdoc. And as I said, I think these, when this video came out, it was very shocking. I think Sang-Bae had said people at DLR were just, blown away that it wasn't breaking the gearboxes, right? And so, I think this type of actuation paradigm is really well suited for managing unplanned contacts and for helping our systems move in a highly dynamic manner through the world. These actuators enable us to have high bandwidth physical interaction through contact. They help us to mitigate impact impulses by being highly transparent, and they have a pretty high torque density. So for every gram of actuator we carry along, we get a bit of torque out of it. In terms of key features here, these proprioceptive actuators, or also known as quasi-direct drive motors, have a high gap radius stator and a low gear transmission. And this strategy of essentially minimizing the transmissions and the transmission dynamics allows accurate delivery of force without external force sensors. So I'm saying here accurate force delivery to mean that we can get forces down to the foot in an accurate way. And I'm going to contrast that with force control, where force control would be something where you take feedback from a force sensor. So we do kind of, in a sense, have co-located force control here, that we have a current monitor on the motor. And so we can use that to get torque control on the motor side, as opposed to at the output. And there's no springs or stiffness modulating mechanisms in this type of a design. You can kind of think of these proprioceptive actuators as phantom robots on steroids. So in these phantom robots for surgical tasks, the goal is to render impedances at the endpoint as accurately as possible so that the surgeons can feel, mock tissues. And so it's really just a scaled up version of that. So how does this compare to other actuation paradigms? Well, let's consider perhaps the most common one, where we've got a motor and a high gear ratio transmission and a stiff torque sensor, and then our high inertial leg. So here, you can do feedback control on this stiff torque sensor, and empirically, we've seen, closed loop force bandwidths 5, I would say probably in more of the recent DLR hardware, probably up closer to 30 in some of them. But these designs are kind of fundamentally not impact robust. That if I were to use a hammer and bang on the end of the leg, there'd be a very large force ripple that would go back through this chain and often excite unintended structural vibrations that really complicate control. So in order to address that, of course, many folks have looked at series elastic actuators, adding a spring in series there. in place of a stiff torque sensor. And by closing a position loop on the deflection of this spring, you can control the torques that are delivered to the leg. I would say 15 up to 30 or 45 hertz, actually, in some of the more recent ones with out of Luis Sentis's lab and the like. So here you get a lot of impact robustness, but you do have to fight this spring. By comparison with these proprioceptive actuators, by really minimizing the transmissions, we get a very high delivery bandwidth of forces, empirically observed up around 100 hertz. And by minimizing the reflected inertia, these designs are quite robust to impacts. So I'd like to take a look a little bit more formally as to why this design performs well. So let's consider a simple leg model. Let's imagine that we have a main body here with mass mb, and a leg mass over here with mass ml, and a rotor with an inertia I. And we'll denote the angle of that rotor with theta. So we're going to imagine this leg interfacing with the ground with a stiffness Ki. And let's consider what happens if I put a torque essentially onto this rotor. How does that map to forces at the feet? Right? Of course, there's some springs in here, so it's not an immediate mapping, but we can look at the transfer function from the torques at this motor to the forces at the ground. And if we do that, you can see that the bandwidth for the delivery of forces, kind of intuitively, here I'm graphing leg mass on this axis, inertia on this axis. Yellow is higher bandwidth. So we maximize bandwidth by minimizing leg mass and inertia. In a similar vein, if we take this system and we pull it up in the air and we drop it down and we look at the maximum force that we see during an impact, in that case, blue here is lower, so low leg mass, low inertia leads to the lowest impact forces. So from this simple analysis, low leg mass and actuated inertia maximize bandwidth and minimize impact forces. So how does this compare, however, when we add a series elastic element in here? So let's put an elastic element Ks in there with stiffness Ks. And now if I look at the open loop mechanical bandwidth from torque at my actuator to force at my foot, I actually have two poles in my transfer function, one graphed here in red, one graphed here in blue, graphing the frequency of the poles in my transfer function as a function of my spring constant here. And so over on the right, you can think the cheetah is essentially a rigid transmission, and this predicts, when we add realistic values for the different parameters here, it predicts that cheetah would have a open loop force delivery bandwidth of around 80 hertz, which is roughly what we see. If you put in a series spring stiffness of 70 Newton meters per radian, which is from one of the earlier versions of Animal from their Starleth robot, it predicts a closed loop bandwidth of around, or an open loop control bandwidth of around 13.5 hertz. And so the point I want to emphasize here is that this is really open loop bandwidth. But if you want to do something that's faster than this with an SEA, you can, but it often takes a lot of control effort. And in practice, we see that the bandwidth for these SEA robots as kind of roughly similar around here. And so the overall observation is that due to actuator limitations, mechanical bandwidth, this open loop force delivery bandwidth, ultimately limits force control bandwidth when you incorporate feedback. So we've quantified these bandwidth numbers, but I haven't really quantified this impact robustness. So we in our paper in 2017, we came up with a way to kind of quantify the capability of the passive dynamics to mitigate impact impulses. Let me try to diagram it for you. So we've got our equations of motion for the robot, and we know that when the robot flies through the air, when its foot hits the ground, there's going to be an impact impulse that's kind of opposite to the impact velocity. And it turns out that impact impulse is scaled by this matrix lambda that's the operational space inertia matrix. It's essentially the effective mass that you would feel at the foot if you were to probe it right before it touched the ground. So we wanted to look at this clearly plays a role in the impacts we see. How can we compare this across robots of different sizes? How can we non-dimensionalize it? So our idea was to take these equations of motion and partition them down into the floating base and these joint components. And then ask the question, what mass do I have at the foot in the worst case? And the worst case might be when all of my joints are rigidly locked and I just hit like a rock at my foot. If all the joints are locked, then essentially these like J components just go away in a sense. And you're left with this worst case locked inertia. Now you can think this locked inertia, it's got to be worse or larger than the regular contact inertia, and you can prove that that's the case. And the implication of that is that this following quantity, this determinant of identity minus lambda times this locked inertia inverse, that this determinant is between 0 and 1. And let me give you some insight into it. In the best case scenario, when lambda is 0, if there's no contact mass and so no impact impulse, when lambda is 0, then I have the determinant of the identity, so I get a 1. So 1 is good, best case scenario. Worst case scenario, if this matrix lambda is equal to the locked case, then I get an identity matrix when I do this multiplication. So I get the determinant of 0, I get 0, 0, which is bad, right? So 0 is bad, 1 is good. So we took a look at these numbers for a couple different actuation paradigms. Here we looked at Hubo first. I'll note that this impact mitigation factor does depend on your knee angle. You can think if your leg is outstretched, if you're closer to singularity, that gives you less ability to kind of absorb the impact than if you have a bent knee. Right? So here's Hubo and here's Cheetah via comparison. So we can see, in the most reasonable part of the workspace, Cheetah is drastically outperforming Hubo. So this shows kind of a more conventional paradigm versus the proprioceptive, but what about those series elastics? So if we graph the series elastics, they do outperform Cheetah a little bit in terms of this impact mitigation, but I'll remind you that, in terms of adding that spring, you're often either adding a lot of complexity in the controller and sacrificing some bandwidth for your force control. So in terms of what this buys you for during control, we did a couple of experiments. This was when I ran down in the lab. So here we had Cheetah run over this load cell that's embedded in the ground. And over here, I'm graphing time on the x-axis, force on the vertical axis, and I'm showing the lateral and vertical force here. And in blue is a desired force from a balance controller. And in red is the force that we're measuring from that load cell. And I'll emphasize here, the robot doesn't have feedback from the load cell. It doesn't have any feedback, it doesn't have a load cell under its feet either. This is just open loop force delivery. And this, it looks reasonably accurate, but I think the more impressive thing here in terms of being highly dynamic is that we're looking at, from 0 to 500 newtons in 40 milliseconds and then back, right? And to put that in context, right? Like the blink of an eye is around 300 milliseconds. So these are just fast dynamics. So what are the benefits of these proprioceptive actuators? They allow you to mitigate impacts. They allow you to deliver forces quite well. The other thing that we found is actually a nice implication for system identification. And that's that these actuators, by minimizing kind of the parasitics in the transmission, actually make our rigid body assumption much better than in other cases when it might be. So we did a test where we tried to identify the Cheetah leg. We slung it around on the table and gathered some measurements for the joint angles and joint rates and the torques at the joints. And then we attempted to identify some of the mass inertial parameters given by pi here, where y is the classical regressor matrix. So we're trying to fit some data and also trying to not stray too far from CAD data here with pi hat. So when you do this, even though you get a somewhat reasonable model, the mass distributions that you get out are just absolutely horrendous. So here on the right is are showing the kind of equidensity contours for the identified mass distributions coming out of this, this identification. And we found this was some work from me, Sangbei, and Jean-Jacques Slotine in 2018, and then followed up in collaboration with Tae-Yoon Lee and Frank Park. Really, the culprit here is this Euclidean regularizer. And we found that we can essentially take that, drop it out, and put instead a new regularizer that's also convex, that has this nice connection to entropy and the KL divergence. If I give you two inertia matrices, I can calculate this quantity, and it's invariant to reference frames and physical units, and so is more sensible than the conventional Euclidean metric, which is dependent on choice of frames. And so with just this very small change, we can get much more sensible results out of our system identification. I think it's really easy to mess up system identification sometimes, and this makes it harder to mess it up. In addition to identifying mass distributions that are reasonable, we also get a really good model out of this. So here I'm showing you the abad and hip angles on the top, and then down here in blue is the measured torque coming out of the motor amplifier, or the predicted torque coming out of the motor amplifier, and in red is the model that we've identified. So essentially we can do inverse dynamics down to about a Newton meter RMS, where a lot of that's just coming from the noise here. Okay, so big picture takeaways. I think when it comes to managing physical interaction and having highly dynamic robots, these proprioceptive actuators have a lot of benefits. They enable high bandwidth delivery of forces, minimize impact loading due to reduced reflected inertia, and this actuator transparency really enables accurate rigid body modeling. Okay. So I'd like to shift gears now and take a look at some of the work we've been doing for optimizing trajectories with these systems that have impacts. In my lab, we've been really encouraged by some of the work that's going on in many labs in Europe and elsewhere that's using differential dynamic programming. And so we've been looking at that as well. I'd like to give a brief introduction to DDP here first, for those that might not have seen it before. So in its most simple form, DDP solves an optimal control problem that's given in discrete time form. So here we've got some running cost and some terminal cost and our discrete time dynamics. And the idea with DDP is that we'd like to be able to find the value function, or the so-called optimal cost to go. And to do that, we'd have to solve Bellman's equation, but we know that we can't do that because of the curse of dimensionality. So the idea in DDP is to instead consider some nominal trajectory and then consider some small change in state and control around it. And so if I take that right-hand side of the equation and I expand it out to second order, I can find a rule that tells me how I should update my controls based on how far my state is away from the nominal trajectory. As a kind of a technical detail, these two quantities, kappa and k, depend on the Hessian and the gradient of the optimal cost to go at the next time step. And essentially, by taking this feedback law and plugging it back in, you can come up with a difference equation that relates an approximation of this optimal cost to go at time step j+1 to an approximation of it at the previous time step. So this explains the name, differential dynamic programming. It's just, rather than solving dynamic programming everywhere, it's just looking differentially around a nominal trajectory. And so we can use that to improve the trajectory and repeat this process until we arrive at something optimal. In its most vanilla form or nascent form, this DDP algorithm only handles these dynamics constraints. They don't handle any more general constraints. And so that limits the ability to apply this algorithm to hybrid systems, as we would like in our legged locomotion work. So we've recently extended this DDP paradigm in order to be able to solve hybrid systems trajectory optimization problems. We consider a problem where the mode sequence is fixed, So I am now looking at some cost functions within each of a number of different modes, and I'm indexing modes by I. We've got different dynamics within each mode. And optionally, you know, if you think for our legged robots, we might have a flight period, and then we come in contact with the ground, and there's an impact. So we include a reset map that is triggered at the end of each segment, setting the initial condition for the next one. These resets just can't happen anywhere. You know, we need to switch to stance when our foot hits the ground. So we need to include a switching constraint in this problem. And maybe there are other constraints like torque limits and that kind of thing that we want to think about too. So what our strategy does is we leverage DDP to handle this innermost loop. And we have a slight extension of it that handles this reset map to provide some impact awareness to our trajectory optimization. And then we address these other constraints via an outer loop. So we've already talked about this yellow part. Let me kind of work my way out through the rest of it. In terms of our impact aware DDP strategy, let's imagine that I've got some continuous dynamics here. We might imagine FI as some flight dynamics. Then we've got our reset map and then some stance dynamics. So we know that during each of these continuous phases, we can use the strategy from before in order to understand how the optimal cost to go evolves through time. But the question is, how do we address this impact event? How do we relate the cost to go after impact with the cost to go before the impact? So we can write out what that cost to go must be in its full generality. And then through a little bit of calculus, we can expand these sides to second order, and we get a nice update equation that tells us how to update the Hessian and the gradient of this optimal cost to go on one side of the impact event to the Hessian and the gradient on the other side. Where here, this matrix J is the Jacobian of the reset map across here. And so here, what we're essentially solving is we're fixing the timing of these modes, and we're going to switch to stance no matter where we're at the end of the flight period. And so that introduces some inconsistency that we need to take care of. The way that we take care of that is through an outer loop that uses an augmented Lagrangian strategy. So here on this graph, I'm showing DDP iterations on this x-axis. On the left, I'm showing the cost of the trajectory, and on the right, the constraint violation. So we see here at the beginning, we have some constraint violation in terms of the system not switching when it's at the ground. We update the Lagrange multipliers, we get a little bit better, and get a little bit better yet after we switch them a third time. So in terms of what this looks like, here's the final solution. The final solution is a hybrid feasible trajectory. At the beginning, we have a heuristic controller that switches from flight to stance at a predefined time. And so it violates that switching constraint that I'm showing here in red. We have this impact aware step that understands how cost information before and after impact is related, but still we haven't addressed the fact that contact needs to happen at the ground. And so it's only when we incorporate these augmented Lagrangian updates that we satisfy these constraints and we have a hybrid feasible trajectory. So we've been looking at using this in my lab to enable the mini cheetah robot that we have and to handle more challenging scenarios. So here's a video from one of our simulations doing some real-time MPC in the sim. And so you'll see here what we're doing is we're solving this trajectory optimization problem in a receding horizon fashion, always updating it as we go. And so here, this green area is an area not to step. You might think of it, green is like a garden that you don't want to step on or something of the sort. So we took these trajectories from our simulation, and we looked at doing sim to real transfer with them using the same DDP gains in our hardware, and we had some really good luck. So here's an initial video with the cheetah. Again, the cheetah's mini cheetah is not allowed to step on this area. And we get really good sim to real transfer. This is, after only a couple hours of testing. So I just want to give a shout out to Naver Labs and the MIT Biomimetic Robotics Lab for loaning us the Mini Cheetah. It's really a wonderful platform. We're seeing them get dispersed a little bit more broadly. Okay, so in terms of main takeaways here, we have this trajectory optimization approach that extends DDP to hybrid systems. DDP is a really fast optimizer, and now we can use it in a more broader class of systems. And when we apply our trajectories on this system that has these proprioceptive actuators, they're easy to model because the transmissions are quite transparent. It really simplifies our sim-to-real transfer. Okay, so we're working on doing real-time MPC right now. We're getting pretty close, and so I hope maybe next time I'll have that to show you all. Okay, so we've looked at our actuator design decisions, our control decisions. For this last part, I'd like to kind of switch gears into something that's a little bit more preliminary, where we're looking at trying to design robots that are easier to control. And we're trying to do that by thinking about the design and the control problem together as one coupled control problem. You know, if you have a Cassie robot versus a an Atlas humanoid, you might adopt different control strategies. And so there's clearly some coupling between these types of problems, and we'd like to formalize how to address some of that. And so to motivate it, I'd like to play this old video from Steve Collins, where he has this passive dynamic walker. And so here, through really phenomenal, meticulous engineering, he's engineered the passive dynamics of this machine quite carefully so that it can walk very efficiently. So in this nominal scenario that it's designed for, this robot is highly efficient. The other thing with these passive dynamics, in addition to it being efficient, there's also kind of a closed loop control aspect to some of these designs, in a sense that if you get the design right, then if there's small imperfections in the floor as it's walking, then the system is kind of passively stabilized by its design. So when I'm thinking about designing passive dynamics, there's these two aspects that I want to capture: efficiency, and also that if there are these perturbations, the passive dynamics help stabilize me, like with the cockroach at the beginning. So clearly, these passive dynamic walkers are great. They're super efficient, but they're not all that useful in terms of where we can deploy them. So, we'd like to kind of get the best of both worlds and push these systems toward a case where they're much more efficient and much more versatile. And, thinking about design is quite heuristic, and it's really tough because there's so many things to consider. So of course here, these two axes are probably pretty limiting. I've already mentioned kind of robustness, but you might think of other axes in terms of cost and the like. So I'll just acknowledge that our current strategy of quantifying a design does have some inherent limitations, but I think can still help push us toward that goal. So in terms of what we've been doing to address this design problem, we've been trying to use some of our tools from trajectory optimization. So traditionally, now, before we were looking in discrete time, now I'm looking in continuous time. If you wanted to solve an optimal control problem, you'd have some cost, some dynamics constraints, maybe some path constraints, and some boundary constraints. And let's imagine, usually you're only optimizing state and control because your design is given. But you could think, we could add in some additional parameters that maybe represent link lengths and motor gear ratios. And if you change those parameters, it's going to change, it's going to change your cost. Maybe it takes more energy if you have a lower gear ratio, or it definitely affects your dynamics, right? But we can add these design variables row into the problem without much issue. So now let's think if we want to design a robot for jumping on a stair, right? If we were to do that, we might parameterize this problem by a couple of values. So maybe the height of the stair, the friction coefficient, the surface angle, and the costs and the constraints, and all the different parts of the problem would be dependent on those parameters. And so if we wanted to design a robot that could jump up one set of stairs, this would be a reasonable way to go about it. But we don't just want to jump up one set of stairs. We want robots to be able to handle multiple different types of environments. And so we've been looking at how we can use some tools from an area of nonlinear programming called stochastic programming in order to design robots that are kind of good at multiple different tasks. So we're going to optimize gear ratios and link geometry. And these things are going to be kind of what I'm going to call stage one decisions. They're things that we decide on first, and then they're fixed. After we make those decisions, we have subsequent decisions at another stage, where if the robot finds itself in a different scenario, it can use different control in each of those cases. So each of those cases is going to be parameterized by some scenarios. And our main idea here is that we don't just want to optimize the performance over one scenario, we want to optimize kind of the expected value of the performance across all of these different scenarios. So here, this P is the probability of a given scenario, and here this gamma is just a shorthand for state and control. So if we can solve this problem, which is essentially solving multiple trajectory optimization problems at once, it's going to put design pressure so that our robot is good at doing multiple things as opposed to just one thing. So we have some preliminary results with a planar monopod here, looking at jumping onto flat ground, a stair, and a slope. And so we first optimized the design for jumping on this flat ground, and then evaluated it on this stair. And here you have that the result in red. Here on the X is time, on the Y is the energy required. So by contrast, if we optimize the gear ratios of the robot, and we optimize them considering all of these scenarios, and then we just test it out on this stair, we find that essentially requiring it to be more versatile enables it to have a lower energy requirement in this case. If we optimize the gear ratios and the link lengths, we get something that takes less energy yet and is a little bit faster. So in terms of the co-designed result, the designed robot completes the task faster, and it requires less energy. I'll note here, this is a relatively simple case. If you think, you're solving multiple trajectory optimization problems at once, one of the real challenges is scalability, and that's something that we've been working on and making some great progress on. So as I motivated with the passive dynamic walkers, we don't just want passive dynamics that are energy efficient, we also want our robots to be robust. We want those passive dynamics to be stabilizing when things go wrong. And so the question I'd like to reflect on is what goes wrong sometimes when we have our legged robots? Well, one of the things that can go wrong is that we come in contact with the world at an unanticipated time. So this is a diagram from Honkai Dai and Rust Headrake that I really like. So let's imagine we've got this a limit cycle here in black, and then with this dashed blue. And if everything goes right, we touch the ground at the intended height, and we reset back onto our limit cycle. However, things can go wrong. We could touch down early and be mapped to something that's off our limit cycle, or we could touch down late and be mapped to something that's off our limit cycle as well. So you can think, if you're designing a limit cycle, there could be bad limit cycles where a small change in terrain height leads to a very large spread in states post-impact. Whereas if you design a good limit cycle, you could reduce the clustering of those states even further. And so our thought was well, let's take a look and see what happens if we do co-design. And hopefully if we do co-design and we have a good design, we can further push down that area where those post-impact states live. So to do that, we pulled out our stochastic programming strategy again, where now the stage one decisions are some design variables, as well as a feedback controller. And we took a very simple strategy of just optimizing a time-varying linear feedback controller. Those are our first stage decisions. And then in our second stage of our optimization problem, we assess the behavior of our controller and our design under a suite of different disturbances. And overall here, this is kind of a single NLP via large-scale trajectory optimization that produces a single robot design that can handle all of these disturbances gracefully. So in terms of looking at that legged robotics application, on the left here, I've got a system that was, it was designed for flat ground, and then we looked at its behavior for this unexpected step, and used a hybrid LQR strategy. And we compared that to this other case where we had robust co-design, optimizing the limit cycles as well as the hardware parameters. And the results were pretty exciting. Over here on the left, if you're not thinking about design when trying to create these trajectories for hopping, you get 108% increase in the cost of transport when you have a small disturbance. Whereas over here on the right, you got a larger disturbance, and because you've designed the system to kind of be robust to those cases, we only see a cost of transport increase of 5% over the nominal. In terms of looking at those post-impact states, here I'm showing you the phase portrait and the pre and post-impact states for the LQR controller. So here in blue are our pre-impact states, and in black are our post-impact states. And I'm showing you here phase portraits for the X position and velocity of the body, the Y position and velocity of the body, and the pitch and pitch rate for the body. So here we got a good amount of spread for the LQR controller. Versus with our co-design controller, we've found a solution that really helps to cluster those post-impact states around the nominal, even when we have these terrain height disturbances. So, I recognize this is, simplified in 2D, but we're really encouraged by some of these results, and we're starting to look at how we can address that scalability piece and push this into 3D. So takeaways, here I'm looking to formalize the process of engineering passive dynamics. And we've first seen how we could use co-design for multiple scenarios to ensure that our passive dynamics are essentially versatile across those. And then we've looked at how we can think about design and control together to ensure that our design is kind of, in a sense, partially passively robust to these disturbances, and that we can soak up the rest through control. Okay, so with that, I'll mostly close this down. Hope I've made the case to you that it's not just design and it's not just control for making our robots contact savvy. We really need to think kind of across the board about these two, and I think there's some untapped opportunities by thinking about these problems together to ensure synergy in their solutions. Before I finish out, I'd just like to say that at Notre Dame, our robotics footprint is growing. We've got 2 new folks that are coming in over the next year, and so we're really excited. And if you're in our neck of the woods, we're 90 minutes east of Chicago. We'd love to show you what we have going on. So thank you all.
Thank you, Patrick. Excellent presentation. Very impressive.
Thank you.
So I'm wondering that, are there any questions from the audiences?
Patrick, I do have one. So you focus on the design, like parameters like gear ratio and coupled with the different control policies. Would you think that modeling, like impact modeling, and then according to that, coupled with that, like impedance control, would also do a good job on, zeta landing and jumping?
Yeah, I think that's a great point. So here, the policies that we've been looking at are like linear state feedback policies that are in joint space. There was some really nice work out of Ludovic Righetti's group presented by Bilal Hamoud earlier this week, where they were looking at optimizing impedances for uncertain terrain interactions. And so I think, yeah, that like the joint space stiff feedback gains map to task space in a often unintuitive way. So there might be, there might be some benefit to looking at different parameterizations for that control policy. And you could certainly do that with the framework that we've proposed.
Mm-hmm. Thanks.
Thank you.
Other questions? If not, I would like to thank Patrick again for the great in-depth presentation and all the details. It's really excellent job. Due to the time limit, we will switch to the next presenter.
Thank you.
Yan Bin from